All right, so here we are with chapter number 2, water. Now, this chapter is very important because I feel like what it does is it really kind of brings you back to Gen Chem 2. Because in organic chemistry compared to biochemistry, everything that you're working in is in an, or working with is in an organic solvent. So you might have something that's dissolved in hexane or cyclohexane or decane. um, you're not really working with water and you're not really working with an aqueous environment. Whereas in biochemistry, you are. Everything is dissolved in an aqueous environment. And so then those substances are going to hydrogen bond with their environment. They're going to gain protons and lose protons accordingly. So that's why this chapter is of the utmost importance. Now, we're going to do a little bit of reviewing some of the properties of water for starters. If you remember, water has some very unique physical properties in that it has a high BP, boiling point, not blood pressure. It has a relatively high melting point, a very high heat capacity or specific heat capacity. So basically, one of the things that you need to remember is like, why is that? And it has to do with the hydrogen bonding network that exists in a water solution, which we'll look at in just a moment. We're going to be able to predict whether a molecule or part of a molecule is nonpolar, whether it is polar uncharged or polar charged. Now, these three groupings are groups that we're going to use for our classification of proteinogenic amino acids. And I think people have a tendency to make a simple mistake um, in that they think about polar versus nonpolar. And if I asked you um, if something was polar or nonpolar, I think that you'd be able to kind of use an example and say like water. Okay, water is polar. Why is water polar? Well, water is polar because it has differences in electronegativities. Okay, so we have polar bonds. And then that kind of brings you back to Gen Chem 1 when you're thinking about, well, this molecule is polar, this other molecule is non-polar, a polar molecule versus a polar bond and everything like that. Um, and that's something that I think that people gravitate towards being able to do, classifying something as polar or non-polar. Now, this next level where we have polar uncharged and polar charged, we're going to look at some examples of those, but one of the things that people have a tendency to make a simple mistake on is they say, okay, well, there's polar, uncharged, and polar charged. Great. Then there's nonpolar uncharged and nonpolar charged. Now, I say that's a simple mistake because if you think about it for just a little bit, you're going to return to the fact that if something is charged, it is polar. It has a pole. It has a positive pole, a negative pole. Whereas something that's nonpolar simply cannot be charged. So that's kind of the entire nature of polar versus nonpolar. So I want you to kind of remember that. But think about classifying and predicting if a molecule falls into one of these three major categories. I want you to identify the various bond types and be able to rank their relative strengths. Discuss why weak non-covalent interactions, although weak, are useful in biological systems. Um, Describe the hydrophobic effect in its thermodynamic driving force. Be able to identify an acid in its conjugate base or a base in its conjugate acid, and write a balanced chemical reaction with water. Now, when we talk about acids and conjugate bases and conjugate acids and um, bases, then we're going towards having a conversation about a strong acid or a weak acid. That's absolutely something we'll do. Now, if that's something that you struggled with in your second semester chemistry course, classifying strong acids versus weak acids, or using a strong acid or a weak acid to predict something like pH of a solution, well then let me know and we'll do some examples, but this might be a need for some extra practice. Understand the acid-base properties and how an acid or base changes as pH changes. So what that is getting at is basically the abundance of an acid or the abundance of a base and the protonation state of an acid and a base or a base. Calculate the pH of a strong acid or a weak acid. Determine the concentration of an acid needed to achieve a certain pH value. Generate a titration curve given pKa values. You have to be able to identify the proper axis labels and then identify the buffering region, equivalence points, and know how to find pKa values. Explain the role of buffers in living organisms. These are all of the things that will some of these are just going to be reviews from previous chapters from Gen Chem 2. But these are all the things that we're going to go through in this chapter. Now here what we've got is, I think, kind of a intuitive drawing. So if you look on the left-hand side, we've got a purple ion surrounded by a handful of molecules, a total of 6 molecules. Then on the right-hand side, we've got a green ion surrounded by maybe 5 different molecules. Now, this is simply a model. This is sodium chloride dissolved in water. We've got our, oopsies, that's not, no. We have each of these water molecules. Each of these water molecules, HOH, each of these water molecules has a dipole. It means we've got a partial negative charge and a partial positive charge up there. Now, based on the positioning of these red balls for our oxygens with those partial negative charges, what can you imagine is this ion at the center of it? Well, if it's NaCl, that would be Na+. Then on the right-hand side, those water molecules have kind of repositioned. So now the partial positive charge for each one of our water molecules is repositioned. And so as a result, this ion over here is our chloride ion. So all of these different atoms and ions positioned, are positioned to kind of stabilize and coordinate with their surroundings. So this is NaCl. NaCl dissolves very well in water. It's a strong electrolyte, so it's going to fully dissociate. So this is what water is going to do. So water is the universal solvent for hydrophilic polar molecules, and it's going to form ion dipoles with ionic species. Now, a strong electrolyte like that is going to go into solution very well. It's great. Now, something that wouldn't necessarily be classified in the same sort of way, an organic compound like methanol all the way up to heptanol. We have a structure of methanol, CH3OH. Then we've got this long alkyl chain and then an alcohol. So it's a total of 7 carbons in OH. Now, if we're going to look at an OH, it's got 2 lone pairs of electrons. And we're going to classify this molecule. We could look at this, and actually, you know what I'm going to do is I'm going to just erase the, actually, I think what I can do is this. Bear with me. Okay, let's see, that's what I want to do. Okay, just 1 second, everyone. Okay, so if we look at this side of the molecule, just the hydroxide group, we see these lone pairs of electrons. These lone pairs of electrons, they're going to have partial negative charges. So they're going to be attracted to positive charges, whether that's a positive ion like a sodium ion or a positive or a partial positive charge like that of another water molecule. But this part of the molecule, sorry, it can interact with water pretty well. And it can interact with water in basically a favorable fashion. Now, if we compare that to, let's go ahead and do some erasing. And now let's switch it. Let's go with this. If we look at this side of my molecule, well, carbon to hydrogen, not a polar bond. Um, do we have any lone pairs of electrons in that carbon or hydrogen? We don't. So that part of the molecule that I've got illuminated right now, you can make a case that this is, if it's not straight up hydrophobic, at very least we can say that this part of the molecule is nonpolar. So now what we need to do is, and so basically this part of the molecule won't interact with the water in a favorable fashion. When both parts of this molecule, and the way that I always kind of look at methanol in particular is I like to look at it and I say, okay, well, almost 50% of it is hydroxide, goes into water well, and then the other 50% is hydrocarbon, doesn't go in water particularly well. But empirically or experimentally, the solubility of methanol is overall pretty good. It's going to go into solution with no real issues. So that kind of gives me to, or that draws me to say, okay, well, as long as about 50% of the molecule is polar, then it's going into solution well, when I'm talking about a short chain alcohol. Now, if I continue looking at this table, I'll see the same thing is true for ethanol. Okay, well, ethanol is a little bit more. It's got an additional, let's see, we got C. Now I've converted my ethanol to, or my methanol to ethanol. Do some erasing. Okay. Well, so now what I can say is, all right, well, you know, as long as 1/3 of my molecule, as long as 1/3 of my molecule is um, is polar, then it's going to go into solution well. Okay, sounds good. And then if I look one more time, and if I look at propanol, I see, oh, that also goes into solution well. So now I'm looking at something like this. Okay, so now I'm looking at as long as 25% of my molecule is polar, I'm going to go into solution well. Butanol, pentanol, hexanol, heptanol. As you can see, there's experimentally determined values for the solubility of these substances. How many moles of butanol will go into 100 grams of water at 20 degrees Celsius? And for methanol, ethanol, and propanol, we had an infinity symbol. So as much ethanol or methanol or propanol as you wanted went into solution. Whereas butanol is as soon as you get to 0.11 or more, well then the remainder, the excess of that butanol is not going into solution. Hexanol, 0.0058. So if you add more than 0.0058 moles, it's not going into solution. So what we see is that as the amount or portion of molecule that is uh, say nonpolar increases, the less soluble the compound is. So that's one of the things that we're up against with this. We want a substance, or the more soluble a substance is going to be stemming from how much of it is polar. And the more non-polar a substance is, the less polar, the less soluble that substance is going to be. So it's important to think about solubility. It's also important to think about the types of bonding that you've seen before. So here what we've got, starting in the upper left-hand corner, we've got a water molecule. We have partial positive charges and partial negative charges. We have a dipole in a water molecule. Now, this molecule has bent geometry, which is another thing that's worth thinking about. Then if we jump down to our next molecule, I really like to, use a couple of model example molecules just to give you a little bit of a sense of, well, this is what this molecule likes. For example, NH3 right here. Nitrogen, and then a total of 3 bonds to it, nitrogen to hydrogen bonds. Now that's 3 nitrogen to hydrogen bonds, and then what else this molecule has is, I'm going to highlight it here, it's a lone pair of electrons on the top of that nitrogen. So that nitrogen has a lone pair of electrons, and that lone pair of electrons can do a couple of different things. But one thing that's really important about this is we might have partial charges indicated here, 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 and here, but this nitrogen doesn't have a full formal charge. It has partial charges, not a formal charge. Is this molecule polar? Absolutely. And that's because it has a lone pair of electrons as opposed to, or a lone pair of electrons and 3 bonded atoms as opposed to 4 bonded atoms. If you remember, 4 bonded atoms, nitrogen like this, NH4. This is your polyatomic ion, ammonium. All right, so if we look at a couple of other molecules, specifically if we look at carbon dioxide, carbon dioxide is a nonpolar molecule, and that's because of the geometry, where these partial charges basically cancel one another out. It's almost a game of tug of war where they basically cancel one another out. Now, in terms of an important part of this class, and that you should become very familiar with and comfortable with, is charge-charge interactions, where you have a negative charge from something like a carboxylate ion and an amino group, which has a positive charge. These two groups are going to attract one another due to their opposite charges. We've also got van der Waals interactions, which are commonly known as, or sometimes referred to as, induced dipoles. You have these groups, these methyl groups that, for all intents and purposes, they wouldn't really attract one another. However, what they have a tendency to do is, this line right here represents two electrons. Are those two electrons stuck in the exact place at all times? No, they're not. So there's movement among those electrons. So sometimes those electrons are super close to this carbon nuclei, in which case this has a stronger partial positive charge. If those electrons over here are right there, well then this is going to be partial negative. So those partial charges will attract one another. The strength of a charge-charge interaction ranges from 40 to 200 kilojoules per mole. A van der Waals interaction is 0.4 to 4 kilojoules per mole. Hydrogen bonds range from 25 to 30 kilojoules. So certainly not as strong as a charge-charge interaction, but they're stronger than they are stronger than van der Waals interactions. Then our hydrogen bonds, one thing to keep in mind is that you absolutely have to have a hydrogen, but then you have a nitrogen, oxygen, or a fluorine also involved. And I would say that nitrogen and oxygen are going to be the ones that you see more than anything else. And so what that means is that if we have a nitrogen here, we could have an oxygen here, or as is shown here, you could have that oxygen going to the hydrogen, going to the nitrogen. There's your hydrogen bond. Now, the last but not least of your important interactions are your hydrophobic interactions, and that ranges from about 3 to 10 kilojoules. Now, these are numbers that I will ask you about. I'll ask you about them relatively, and then I'll ask you, what was the range of this? Is this one 50 kilojoules or is this 10 kilojoules? So I do want you to keep these numbers in mind. So this slide shows us on the left-hand side a couple of water molecules. So here's one water molecule, another, and another. I'm going to erase my markings just because otherwise it's even more confusing. So this is 3 water molecules, and basically the hydrogen atoms and oxygen atoms, hydrogen, oxygen, hydrogen, oxygen. And so these atoms are attracted to one another due to a lone pair of electrons or lone pairs of electrons on oxygens, and then hydrogens just kind of attraction to lone pairs of electrons, and attraction to electrons. So these are hydrogen bonds that exist between 1, 2, and 3 water molecules. Similarly, below we've got 1, 2, 3, 4 water molecules, and below that we've got 1, 2, 3, 4, 5 water molecules, and a hydrogen bond network that exists between all of those different atoms. Now, what this is just showing is that the proximity that exists between water molecules, it's going to be kind of the same. The distance and the length of a hydrogen bond is going to be kind of the same, and you can add more molecules, and those molecules will change. Now, what that will also go on to show is a network and a complex network like this, where we have tons of water molecules that they basically form like a multi-dimension network. It's almost like these 3 right here are on one flat plane, but that above that plane right here is another network of 3, and then another network of 3, and another network of 3, and it just goes on and on and on and on, making hydrogen bonding very intricate and a system that has tons of different players involved, where we have these different atoms that make this complex kind of mesh network of sorts. Now, it's this hydrogen bond network that does a number of things. It gives water tons of unique properties like a high boiling point, high specific heat capacity, a high surface tension, a high melting point. Basically, any unique property about water's strength is going to be derived from or connected directly to hydrogen bonding networks. And so that's one thing that you need to think about. This is the solvent in which we're doing basically all of our biochemical reactions. Now, in addition to that, you got to think about, well, molecules can interact with this environment. Some of them, that's great. But then others, the way that I always kind of think about it is if you have a small molecule that can hydrogen bond with itself or it can hydrogen bond with that aqueous solvent, that aqueous solvent is like the big thing. And it can, the way I always kind of visualize it is that that big thing can rip up that small molecule. So it's just something that I think is worthwhile to be thoughtful of. And one example that I always think about from my own personal like lab experience as a graduate student is I always think about the strength of, now we've got weak interactions in biological molecules as well. So here what we've got on the upper left-hand side corner is we have a protein. And that is depicted by this kind of blue line, which I'm writing over with red. And let's just for the sake of simplicity say that this is the backbone of this protein. And there's two amino acids, two proteinogenic amino acids, glutamate and arginine. Now, those names, you'll have to know those names and you'll have to know those identifiers in due time. But for the time being, what we want to focus in on is we want to focus on the side chains. So these side chains right here and right here, respectively, are the parts of an amino acid that are kind of unique. And these parts are going to interact with one another. Here we've got a negatively charged glutamic acid and a positively charged arginine. These two side chains will interact with one another, and those interactions are simply due to, well, opposite charges. Now, if we remember from one of the previous slides that we looked at, it's important to think about approximately how strong is this charge-charge interaction. Well, this charge-charge interaction ranges from approximately 40 to 200 kilojoules per mole. Okay, now I think that's worthwhile to think about. And what I want you to take a moment to do is think about, well, how could this interaction be modified or be different? Well, one way that this could be different is if we didn't have a glutamic acid here. If instead we had an amino acid that was just like this, CH3, a methyl group. Is that methyl group going to interact with this arginine? No, it's not. And so are these two sides, I'm going to label it side A and side B of this protein, are they going to be attracted to one another? They're really not. I think that's an important thing to think about because when you think about mutations, genetic mutations, this is sometimes how they manifest themselves. It might be like there's this minor mutation that causes this huge difference in the protein's function in the sense that it might not catalyze reaction A. Alternatively, it might be that the reaction can no longer be catalyzed because this part of the protein is no longer near this other part of the protein. So charge interactions ranging from about 40 to 200 kilojoules per mole are seen in proteins. Next up, we've got a molecule of cellulose. And in this cellulose, we've got, I know that this is cellulose because this sugar right here is glucose, and we have a beta linkage, and then another beta, 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 beta. Now, what these beta linkages enable cellulose to do is it enables these strands of cellulose, which I'm going to label A, and let me erase my markings from the figure above. I've got A and B. Okay, so with A, we've got something that looks a little bit, no, I'm not going to draw like that. We've got one strand that looks like this, and then another strand that looks like this. And these two strands can basically hydrogen bond with one another. These two groups are going to hydrogen bond. These two groups, these two groups. These groups can all hydrogen bond with one another and basically be super close and super packed in. Um, so that would be hydrogen bonding. We also see hydrogen bonding in DNA. We got hydrogen bonding here, 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 and here. Then we also have, and so our hydrogen bonds, if I remember correctly, our hydrogen bonds are approximately 25 to 30 kilojoules per mole, which let's look at that unit for a second. This is kilojoules per mole. Okay. Now, this, a single ion interaction or a charge interaction, a single one of them is going to be fairly weak. However, 1 mole of them, it will take approximately 40 kilojoules to break 1 mole of that interaction. Now, if you have 1 mole of protein with one of those bonds, then you have 1 mole of that interaction. If we compare that to a molecule like DNA, well, in a DNA molecule, you're going to have hundreds upon thousands upon millions of these hydrogen bonds. And so if you have 1 mole, or let's say, erase some more things just so I can keep my thoughts and ideas organized. I've got one DNA molecule, and that has 60 H bonds. Okay. Now let's say that I have 1 mole of this same DNA molecule. So I'm going to just draw a line, 1 mole of that. Well, that means you actually have 60 moles of hydrogen bonds. So it's going to take it's going to take 60 times 25 to 30 kilojoules in order to break all those hydrogen bonds. So this goes back to individual bonds are not strong. They are relatively strong to one another. You know, a charge-charge interaction is stronger than a hydrogen bond interaction, but if you have, well, if you have a mole of hydrogen bonds, that's even stronger. Okay, so now let's go over here in the lower right-hand corner. We've got a couple of different molecules. We've got sphingosine, sphingomyelin, and ceramide. Now, what's significant about all of these molecules is that they have this long hydrocarbon chain. Now, I like to highlight this and take you back to when we were talking about our different alcohols, when we talked about methanol or ethanol in water versus butanol or decanol or something like that. Heptanol, I think is what we got up to. Well, that heptanol has that long hydrocarbon chain and a single hydroxide group. And its solubility in water is super low compared to that of methanol, because methanol can hydrogen bond with the solution, whereas heptanol cannot. Heptanol is not going to go into solution very well, much like these molecules down here. They're not going to go into solution very well. Sure, there's a hydroxyl group there, maybe even a positively charged group there. But the vast majority of this molecule is going to be nonpolar. There's some portions that are polar, but most of it's nonpolar. Now, with that in mind, these groups, which I'm going to label as 1, 2, and 3, they are going to be loving any sort of hydrophobic region or any sort of hydrophobic group. So they're going to go into a hydrophobic region very easily, and they are not going to go into an aqueous environment very easily. So that's one thing whenever you look at a molecule, think about what does it have and what is that likely to interact with. So the hydrophobic effect is something that you've probably pieced the terms together. You've probably heard it before, you've maybe even been introduced to it, um, but I think that it deserves a little bit of a refresher. So whenever you think about the hydrophobic effect, or whenever I think about the hydrophobic effect, personally, I always think like, okay, well, how is the hydrophobicity of a molecule going to affect its existence in an aqueous environment? So that to me is an important part of it. So hydrophobic compounds are typically going to be polar or nonpolar. Well, hydrophobic compounds are typically going to be nonpolar because a water-fearing molecule is going to be unlike water. And water as a polar molecule is, well, sorry, a polar molecule is more than likely going to be hydrophilic, so it's going to go into solution very well. Opposite of that would be a nonpolar molecule, which is going to not be water-loving, so it's hydrophobic. Next up is a hydrophobic compound. Is it going to be soluble in water or nonpolar solvents? Well, a hydrophobic compound is not particularly likely to be soluble in water, but it's more likely to be soluble in nonpolar solvents. So this takes you back to like dissolves like. So a substance that is nonpolar is going to go into solution well, so long as that solution is nonpolar. Now, water tends to minimize its contact with hydrophobic molecules. This is the hydrophobic effect. So when we have compounds, and our biological compounds that really fit this billing well are fatty acids. So let's say that this is one fatty acid, here's another fatty acid, and let's say that we've got water molecules, which I'm going to switch the color. Say that this is a water molecule here, 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 here. Bunch of water molecules. Okay, so all of those water molecules are making contact with all of the sides of those fatty acids. Now, those fatty acids, and this is something you've probably seen before, like if you've ever poured a little bit of bacon grease or something like that, or not even bacon grease, like vegetable oil. If you pour vegetable oil, put a droplet of vegetable oil in water, what's going to happen to it? Well, that vegetable oil is kind of like move around. Then if you put a second droplet of vegetable oil in there, what's going to happen to that second droplet of vegetable oil? Well, that's also going to float around, and then at some point they're going to come in contact, and they're going to it's almost like they've formed something together. And that's what we see happen with hydrophobic compounds. Like what I've got on my left-hand side of this is here's my first droplet of that vegetable oil, and here's my second droplet of vegetable oil. In time, what's going to happen is that these two are ultimately just going to gravitate towards one another. And they're going to basically take all those water molecules that separated them and force them away. So we get something like this, And now I'm not sure if I picked the right, I think I did, the right hue of water. And the same number of water molecules are present, but they're no longer going to be dividing our two hydrophobic compounds because those hydrophobic compounds, almost more than anything else, want to be right next to one another. So this is water minimizing its contact with the hydrophobic molecules. And just so I'm going to kind of belabor this point, but if you think about it, I'm going to redraw my models here. Redraw my molecules. Okay, so here's one molecule, and here's another hydrophobic molecule. If we have water on this side, this side, this side, this side, this side, this side, and arguably, yeah, here we go, up top as well. So we have a pair of molecules with a total of 8 surfaces, 8 sides of these molecules that are in contact with water. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. So 4 plus 4 is 8. Now, that's what we have in the absence of the hydrophobic effect. But what we observe is the hydrophobic effect. It is a real thing. So now what's going to happen is those two molecules are basically going to be kind of forced up next to one another. There's one, there's my other one. And now what I'm going to get is 1, 2, 3, 4. So 1, 2, 3, 4. So rather than there being a total of 8 sides in which our water was contacting our hydrophobic molecules, the hydrophobic effects helps us reduce that from 8 to 4 with these two molecules. So yeah, the hydrophobic compound is being contacted on all 4 sides, but it's not doubling it by keeping these things separate from one another. Okay, so what we also see is the transfer of nonpolar molecules away from water to other nonpolar molecules or solvents, and that is a spontaneous process. So on the next slide, we have a nice visual of what's taking place. We have our two nonpolar molecules that they have solvation spheres around them. They have these water molecules that have formed these nice kind of fences around them of sorts. And then those nonpolar molecules basically aggregate together and give us something like what we see on the right-hand side. The water surrounds these nonpolar molecules, and rather than there being two separate ones, there's one kind of contained thing. Okay, so this is going to be a little bit of Gen Chem 2 stuff. And I know Gen Chem 2 is a tough class. I had my own experience as a student taking Gen Chem 2, and it's a tough class. So there's many things from Gen Chem 2 that I'm like, oh, if I don't have to see that again, I'm going to be pretty happy about that. But this is absolutely important because we have to think about how different reagents and different molecules react in water and how they change. So here what we have is some scenarios for how, well, or a scenario for how two water molecules react with one another. And if you remember, this is sometimes referred to as our autoionization of water. So if we have water molecule 1 reacting with water molecule 2 to form this and this. Okay, our products, H3O plus and OH minus. Okay, now one thing that I want to do is I want you to think about this water molecule number 1. What is it doing? This is water molecule 1 versus water molecule 2. Water molecule 1 is picking up a hydrogen ion. So 1 gets H from H2O. That means that water molecule 2 gives up H from itself. So when you think about that terminology, or you think about that process of getting a hydrogen ion or gaining a hydrogen, well, effectively what that means is the one is going to be acting by gaining a hydrogen. So it gains a hydrogen, so it acts as a base. And then 2 donates H, so acts as an acid. All right, so that brings up this question at the bottom. So this brings us back to, sorry, this is water acts as an amphiphilic uh, molecule. It can act as, sorry, not amphiphile. Water is amphoteric. Amphoteric. Acid or base. And acid and base for that matter. So this question at the bottom though, what is the KEQ for this reaction? Okay, so when we're writing KEQ, we want to say KEQ equals our products. So concentration of our products, which our products are H3O plus, which is the hydronium ion. Sometimes you'll see that just written as a hydrogen ion. And I'm going to say that H plus and H3O plus are completely interchangeable. And then I'm going to say OH minus. And then I'm going to divide this by the concentration of my reactants, which is H2O. And then H2O. And then I'm going to say, aha, but in Gen Chem 2, I learned that I do not have to include H2O. And in fact, I do not include H2O or a solid. So essentially, I get a KEQ, which is H3O plus times the concentration of H3O plus, or the concentration of a hydrogen ion, or of the hydrogen ions, times the concentration of hydroxide ions. So there's my KEQ for this reaction. Now, one of the important parts about this class is understanding that we are dealing with an aqueous environment, so we do need to be thoughtful of strong and weak acids. Now, we'll predominantly be working with weak acids because we're working with amino acids. And we're going to, and so what that means is that our difference between strong acids and weak acids is that whenever you have a weak acid and you add it to water, sure, you still generate hydronium ions and you generate that conjugate base of your acid. But the biggest difference is that if you have acetic acid, I always like to give myself round numbers. Let's say I have 100 copies of acetic acid and I add that to water and I let it sit and it reaches equilibrium. And let's say that for the sake of, um, let's just say I give myself 10 minutes, or I give this reaction 10 minutes to reach equilibrium. Well, after 10 minutes, I'm still probably going to have about, rather than 100, I'm going to have about 90 molecules of acetic acid. But then what do I have over here? Well, I've probably got about 10 CH3COO minus, 10 of these, and then I've got 10 hydrogen ions. Whereas if I had HCl and I added that to water, If I had 100 copies of this, well, after 10 minutes, I'm going to have 0 of HCl, and I'm going to have 100 of this, and 100 of this, because that will completely dissociate. That's the nature of a strong acid. Now, what we'll be doing a lot of is looking at titration curves and processing and understanding titration curves, understanding the different components of a titration curve and what do they show? What species are present at a given pH provided with this titration curve? Now, there's a lot to unpack with this equation right here. This is our Henderson-Hasselbalch equation. And this Henderson-Hasselbalch equation, I remember whenever I saw it as a student in Gen Chem 2, it was like, oh man, this makes things considerably easier. And I think that that is true. Um, a couple of things to unpack from it is this lowercase p in front of H and Ka corresponds to the negative log of the concentration of hydrogen ions. Okay, and then this negative pK, or this pKa stands for the negative log of AKA. So with that in mind, I think that it's good to look at kind of the third component of this equation. That third component is this right here. So that third component is the ratio of a deprotonated form of a molecule versus the protonated form of the molecule. Now, I think that it's always really important to think about any acid. And let's take a couple of different acids. Let's take acetic acid. Acetic acid is CH3COOH. Now, that is going to correspond to my HA. Well, if that's what corresponds to HA, then what corresponds to A minus is CH3COO minus, the acetate ion. So acetic acid versus acetate. Now, that is a little bit easier than what are some other options? One other option or one other acid that you could compare this to would be something like, let's go with um, let's go with phosphoric acid. Phosphoric acid, H3PO4. Now, most folks, what they can do is they can see H3PO4 and say, aha, H3PO4, done. Phosphoric acid is the HA. Now, what is the difference between HA and A minus? Well, it loses a hydrogen. So how do you apply that to something like phosphoric acid? Well, you say H3PO4, but lose an A. I'm sorry. And that would be H2PO4. But also, when you lose that H, you got to include that negative charge there. So H3PO4 becomes H2PO4 minus. Okay. Now, the next level to that is, well, H2PO4 in and of itself can correspond to the HA, in which case, what would then A minus be? Well, that would be HPO4 2 minus. So there is your negative 2 charged acid. So all of these acids vary a little bit, and they vary with respect to their strengths. But the Henderson-Hasselbalch equation is asking you about concentrations of different species of an acid and comparing that to a pH. You can also be asked about, well, given concentrations of these species, what is the pH of a solution? Now, with that in mind, this is so important because when we talk about proteins and amino acids, we're looking at, well, which form of that amino acid is present in? Is it the doubly protonated? Is it singly protonated? The non-protonated? Which form of that acid is present? Then there's a certain situation whenever pH is equal to pKa. I'll give you a second to think about that. When would pH equal pKa? Well, that would be whenever this whole species right here, this part of the equation, equals 0. When could that equal 0? Well, when log of A, or sorry, when A minus and HA are the same. So log of, let's say 0.5 over 0.5. Those two are equal to one another, so that effectively is going to be 0. So log of 1 equals 0. So there are instances where you would have an equal abundance of H3PO4 and H2PO4 in a reaction. When you have equal concentrations of those, then you're going to have a charge of, or you're going to have, when you have an equal abundance of those, then your pH is going to be equal to the pKa. Now, I like this table that we showed below because it's got our Kas, but then it also has our pKas. So I'll give you this as an example. If you had an equal concentration of H2PO4 minus and H3PO4, so let's call it 0.5 molar, 0.5 molar, what would the pH of the solution be if you had equal concentrations of those? The pH would be approximately 2.2 because that's what our pKa is. Now we're going to get into a lot more examples of these, and we'll get into a lot of examples with amino acids, proteinogenic amino acids. But for the next little bit, I want you to pay a lot of attention to this and make sure that you feel good about doing these sorts of analyses and these sorts of calculations, because this is going to be a huge part of the content on your exam that relates to this, but also understanding amino acids and identifying in a solution, well, how much of this amino acid is present? How much of the protonated form of this amino acid is present? So just be thoughtful of all of that. Okay. Now, here again, we have acetic acid, and that acetic acid will dissociate into a hydrogen ion and CH3COO minus, or acetate ion. Now, if we have a pKa for acetic acid of 4.8, that would be right here. That means that we have 50%, or we have an equal concentration of CH3COOH and CH3COO minus. So we have an equal concentration of our protonated and our deprotonated form of this acid. Now, what that means is that on this side, where I put my X, what is more concentrated? Or what do I have a greater concentration of? The acetic acid or acetate? This to me is one of the most important parts about understanding amino acids and their ionization. Well, at a lower pH, what do we have? Low pH gives us that means high hydrogen ion concentration. And if you have a high concentration of hydrogen ions, what are those hydrogen ions going to do? Well, they're going to look for negative charges. They're going to look for groups that they can jump onto, and if they can jump onto them, they're going to. So if you have a high concentration of hydrogen ions, then you would expect to have a lower concentration of CH3COO minus. Because of the fact that, well, wherever there are these hydrogen ions are going to say, okay, fantastic. We're going to together make a CH3COOH. Done. Meanwhile, at a higher pH, then you would expect to have a low hydrogen ion concentration, so you'd have a lot of these to the right, or at a higher pH. We're going to go ahead and draw a titration curve for phosphoric acid. And we're going to do a couple of things with this titration curve. So first thing that I want to do is I want to label my y-axis. I'm going to label it as pH. And I'm just going to go ahead. Oh, I'm not good at drawing straight lines sometimes. Erase that. There we go, that's better. That's better. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, now I've got my pKa values. I've got my different acids. And my x-axis, what I'm going to do is I'm going to extend that a little bit farther. And I'm going to give you labels that maybe are a little bit confusing. So on the x-axis, I'm going to label it 0.5, 1.0, 1.5, 2.0, 2.5, 3.0. Okay. The next thing that I'm going to do is I'm going to pick out my pKa values. I know that my pKa values are where I have an equal concentration of two different species. So I have a 50-50 combination of this species and this other species. So what I'm going to do is I'm going to take this 2.2 and I put my label right there. So I'm going to post up my pKa's first. So I'm going to find 0.5, my low pH pKa value, my low pH 50% spot. Then I'm going to get my next pKa value, which is 7.2. That 7.2, I'm going to look for my next 0.5. So the first one is 0.5, the next one is blank 0.5, and the next, after that, the 12.7 is going to be blank 0.5. Well, what number comes after 0? 1. 1. Yep, it's 1. So 1.5 is going to be my 7.2. There's that. And then what number comes after 1? Again, you're right. It's 2. So I'm going to label the 2.5 as 12.7 approximately, right there. Now, what I think is helpful is to say, all right, well, I'm going to look at ionizing each one of these groups, and so it's going to be my group number 0 is going to be this first hydrogen ion. Then the next one is going to be the second hydrogen ion, and then the next one is going to be the third hydrogen ion. So this first group is completely deprotonated whenever I've hit 1.0 or it's 100% deprotonated. The next group is going to be 100% deprotonated whenever I hit my next 100% or 2.0. Then my next group is going to be deprotonated whenever I hit 3.0, which is my last 100%. So I'm going to draw a titration curve that looks a little bit like this. I'm going to start out low, and then it's going to plateau. It's going to have a horizontal region, and then it's going to go up oh so gradually. And then as soon as I hit 1.0 or get close to 1.0, it's going to go up pretty steep, and then it's going to begin to plateau again. Now, this isn't really a radical new thing with respect to drawing titration curves. You've done this a number of times. And that just so happens that I wrote pKa there, so I'm going to erase that. But this effectively is my titration curve. Okay, so if this is like the first part of it, then I think what we should do is break it down a little bit further. Okay, so what I always like to do whenever I'm drawing a titration curve is I'll draw a line 1.0, my 2.0, my 3.0. Now, if I was really good at drawing, especially drawing on a tablet, then my lines would be completely straight. But I think that you get the point where we're going. So there's a couple of things to think about. When we are at this point on our titration curve, basically at the origin, which one of these different molecules, one, two, or three, is the most common or the most abundant form of my molecule? At the lowest possible pH, phosphoric acid is the most abundant. The fully protonated form of my molecule. I have so many hydrogen ions or protons there that they are going to, well, I've got H3PO4. So at an infinitely no, sorry, an infinitely low pH, I've got nothing but H3PO4 there. Okay. Then at my other end, over here, well, at my highest, I've got that HPO4 minus. Now, with that in mind, that is where things are going to, so that's kind of my extreme. So, excuse me, between this point or the origin and this point way over here, I'm going to be deprotonating my molecule. Now, the different places in this titration curve, I'm going to label them as 1, 2, and 3. Now I'm going to do some erasing. I'm going to get rid of that HPO4. I'm going to get rid of this right here. And now I'm going to do a dashed line at my 0.5. At my 0.5, I have an equal abundance of these two acids. I have an equal concentration of H3PO4 and H2PO4 minus. At my next, my next 0.5, I have an equal abundance of H2PO4 minus and HPO4 minus. Now my third and my last one, or my third and final one, is where I need to kind of go back. I have an equal abundance of HPO4 minus, and this is where I need to make an addition of PO4 3 minus. So at this point, I don't have HPO4, but I have PO4 3 minus. So the way that I think is helpful to think about that is you are slowly but surely converting H3PO4 into H2PO4. Then you're going to, as you're increasing the pH, you're slowly but surely converting H2PO4 to HPO4. Then as you continue increasing the pH more, you get PO4 3 minus. So whenever we're, like, let's say right here on the titration curve, I'm going to do some erasing. Whenever we are at this particular location, I'll fine tune that a little bit. Whenever I'm right here, and then I'll come up with a little bit better of a number. Let's say that my pH is 12.9. So my pH is higher than 12.7. I know when my pH is 12.7, I have an equal concentration, 50% HPO4 2 minus, and 50% the deprotonated form of that PO4 3 minus. So that's whenever it's 12.7. But what about when my pH is 12.9? That's more basic. So what that means is I have a little bit less of HPO4 2 minus. When you have less HPO4 2 minus, that means you have more PO4 3 minus. Okay, so let's go ahead and just for the sake of simplicity, we can give ourselves a round number and say that it's, 65% PO4 3 minus, and that would mean 35% HPO4 2 minus. Now these are numbers that you can come up with using the Henderson-Hasselbalch equation. And you can just punch in a ratio. So that's what we're going to do here. So when I got to find the space for it. I've been drawing all over this slide. So let's erase my axis, erase this. Now I'm going to say when my pH is 12.9, my pKa is 12.7 plus log of something over something. So that's going to be minus 12.7. So 0.2 equals log of, and this would be A minus over HA. So what we need to do with this is we need to take this 0.2, this log of A minus over HA, and we can kind of not really, what we know is that the A minus, the deprotonated form of our molecule, is going to be more abundant. So what I'm going to do is I'm going to say raise both of these things to 10 or 10 to the this. So I can get rid of that log. So whenever I raise 10 to the 0.2, I get 1.58 equals concentration of A minus over HA. Now that doesn't help me a whole lot. However, what I can say is now I can plug in 1.58 and switch these to put this A minus and HA in terms of X. So I'm going to say 1 minus X over X. Because I know that these two quantities are going to add up to be 1. And so I'll multiply each side by X and I'll get 1.58 X equals 1 minus X. Then I'll add X to each side. That will give me 2.58. X equals 1. I'll divide each side by 2.58. And that's whenever I'll arrive at approximately 0.39, I think is what I got. So X is equal to, now I'm going up into the upper right-hand corner, X equals 0.39. So what does that mean for my concentration of A minus? Well, that is going to be 1 minus 0.39. So concentration of A minus equals 0.61. So I have a concentration of 0.61 over 0.39, which aligns with what I expected, or gives me what I kind of expected. that my concentration of my deprotonated form, my PO4 3 minus, is greater than that of my protonated form. Now, a follow-up to this is to think about phosphoric acid. When we're at a pH of 12.9, approximately how much phosphoric acid is there? Oof, that's tricky. We just looked at this and said effectively our deprotonated form was 0.61 or 61%, and then our protonated form was about 39%. And the truth is, there's basically no H3PO4. There's basically no H2PO4. Now, is it absolutely zero? No, it's not. But the amount is basically insignificant. And these quantities of H3PO4 and H2PO4 minus don't really have a big impact on the pH of my solution. So you could look at this and say H3PO4 and H2PO4 minus are basically not present in that solution in any significant amount. HPO4 2 minus and PO4 3 minus, they are present, but H3PO4 and H2PO4 minus are not. Now, buffers. This brings up kind of a I'm going to just draw a titration curve. I'm going to draw a titration curve for a diprotic acid. So it's going to look like this. 1 pKa, here's a second pKa. So 0.5, 1.0, 1.5, 2.0. Now, let's say that we're talking about, let's see, what's a good diprotic acid that I could use? The only ones I can think of are amino acids, and I don't really want to use amino acids at this point in time. But when we think about a buffer, it's valuable to think about a buffer and our definition of a buffer. A solution whose pH will not change dramatically when strong acid or base are added. Okay, so the addition of a strong acid or a base isn't going to change the pH. And you know, now that I think of it, I can do this with a monoprotic acid just as well. So let's say that we have a monoprotic acid like acetic acid. It's got a single 0.5, 1.0, 4.3 is where my pKa is. My y-axis is my pH. It's either 4.3 or 4.7. I think it might be 4.7 now that I think about it. Yeah, 4.8 is what we had on the previous slide. So pKa of 4.8. Acetic acid, CH3, COOH, and CH3, COO minus. Well, you can make a buffer from acetic acid because you have an acid and a conjugate base. Okay, so you have a balance of these two species. Now, the thing is, you have to be thoughtful of basically how much is in this acid or base, or how much of acids and bases are present in here. when it comes to a and when you are trying to maintain a buffer, let's say a buffer at a pH of 7. If you wanted a solution with a pH of 7, acetic acid and sodium and acetate, that would be a bad combination. Because if you have acetic acid and acetate, and you have equal combination or equal amounts of them, they're going to get a pH of 4.8. That's going to be great. It's going to hold the pH at 4.8. You can add some HCl, and what's going to happen is the amount of acetic acid, that's going to go up a little bit, and the amount of the conjugate base is going to go down a little bit. You're going to end up like right here. You can add some more HCl. You're going to end up right here. Add more. Boom, boom. You're making these small amounts. At some point, that buffer you'll exceed the capacity of that buffer. And then your pH is going to drop off a whole lot. Your pH is going to be like 2.1 or 1.2. It's not going to be a buffer anymore. And you can add like half a drop of strong acid, and that pH is going to go from 2.7 down to 2.1 very rapidly because that's outside the buffering range. Whenever you're making a buffer, determine the pH that you want to make that buffer at, and then find a acid and conjugate base pair that give you a pKa close to that desired pH. So if you wanted to make and if you wanted to make a buffer with a pH of 4.8, acetic acid is perfect because you can add acid or you can add a strong base like sodium hydroxide, and the pH isn't going to change very much. This will function, and this will be a good combination to hold the pH as low as 3.8 to as high as 5.8. If you go outside of this, it's not going to be very good. But within that range, this is going to be perfect for what you're looking for. So with that in mind, be careful whenever you're selecting what buffer you want to use. As a general rule of thumb, find the pKa of that buffer and say, okay, well, this can hold the pH plus or minus 1 unit from there. But above that or outside of that, it's not going to be a good situation. All right, well, the last thing that I want to say before we wrap this all up is kind of a preview for when we start talking about amino acids. And that is right here. So I'm going to use my eraser tool. Got some, oh, I didn't want to do that, but oh well. Okay, so another way to look at a molecule like acetic acid and acetate is to look at them and kind of describe them with respect to their charges. So CH3COOH, that is our protonated form of this molecule. It is protonated, but it is neutral. It has no charge. Acetate, on the other hand, CH3COO-, that is our deprotonated form, and that deprotonated form has a negative charge. Don't fall into the trap of saying, oh, protonated means positive. No, protonated means it has a proton. A proton has a positive charge, but that's all that it means. Deprotonated means that it does not have a proton. That means it is lacking a positive charge. So that could mean that it's neutral. That could mean that it's -1. That could mean that it's -2. You have to think about what this molecule kind of started as and where it is now. All right, well, that sums up the important parts of water and the foundational pieces that you need to know for this chapter. We are going to be applying all this information in the context of amino acids in the coming days. Amino acids are, you have to know the structures, you'll have to know, you'll have to know the structures, you'll have to know the identifiers, but lots of the questions that I love to ask regarding amino acids come back to this. So this water chapter is absolutely important for that reason. All right, well, if you've got any questions, please don't hesitate to send me an email. Thank you.